All right, today's notes for section 3.1 of Algebra 2 involve solving systems of equations. We have several different methods for solving systems. Today's focus will be on using tables and, most importantly, using graphs. When you have two or more related unknowns, you may be able to represent their relationship with a system of equations. A system of equations is just a set of two or more equations that we have to solve simultaneously. So to solve a system of equations, we have to find a set of values that makes both equations true. So our first problem, we have the system of equations negative 3x plus 2y equals 8 and x plus 2y equals negative 8. The first method we're going to look at is how to solve them using a graph. Now, the two equations that we are given here are in standard form. So if we were going to graph these by hand, we would want to convert them into slope-intercept form or to find the x and y intercepts. So let's look at the first one. We've got negative 3x plus 2y equals 8. If we were going to solve this for y to put it in slope-intercept form, we would have 2y equals 3x plus 8, just adding the 3x to the right side. And then if we divide everything by 2, we now have it in slope-intercept form. So we're going to start this graph with a y-intercept of 4. The picture I have is just a portion of our graph. So if we think of extending this, all right, we'd have to start this line up here at 4. We just cut off part of our graph. All right, so we would start at 4, we would do a slope of 3/2, and that creates the red line in this picture. Our second equation, x plus 2y equals negative 8. Again, we could do a t-chart and find the intercepts, or we could solve for y. All right, this time we have a line with a slope of negative 1/2 and a y-intercept of negative 4. So looking at our picture here, we have a y-intercept of negative 4, a negative 1/2 slope. We could go up 1 and back 2, creates that equation, or that graph. And what we're trying to do now is we're trying to figure out at what point do these two lines intersect. The point that they have in common, in this case, this point right here, negative 4, negative 2, is the one spot that is shared by both lines. So when we talk about solving a system of equations, this one in particular, we are looking for that point where they overlap, the point they have in common. So our solution to this would be negative 4, negative 2. The second option for solving that is to use a table. And we have our calculator, graphing calculator. So go ahead and in the y equals screen, go ahead and enter these two equations. I want you to enter them this way, solved for y. All right, I'm going to pause the recording and let you get that done. Okay, I've pulled up the graphing calculator here so we can see what I'm talking about. We needed to enter the two equations in our y equals screen. So to get here, I just hit the y equals key. Now notice that we still have the stat plots turned on from our last chapter. So the first thing I'm going to do is go up here, highlight where it says plot 1, and hit enter. It will turn it off, and now I can just arrow down to the first equation. We don't want stat plots on when we're trying to graph other equations because it's going to constantly look for that data and try to graph it. So our first equation was y equals 3/2 x plus 4. To enter that, I'm going to have, I've already got the y equals in there. I need to put in the 1.5 or 3/2. My x key is right here next to the green alpha key. That's my variable x. And then I need the plus 4. Okay. Second equation we wanted to enter was y equals negative 1/2. So negative 0.5 x minus 4. Okay, we have our two equations in there. The second thing I should do, if I want to look at their graphs, would be to make sure I've set the window correctly. Now we've been changing the window from all of the different linear regression equations we've been working on. So a fast way to reset your window is to do a zoom. It's up here in this top row of buttons. Do zoom 6. It resets it to a standard window. And now we can see those two lines that I had graphed earlier in the lesson. To use a table, we've put our equations now in y equals. If we go to our table, which is second graph, I'm going to go back here, second window table set, and I need to change this to automatic. All right. Now we can go second graph to our table, and we've got this list of numbers. All right. We have basically two different t-charts here. Notice that the x values in black apply to both y1 and y2. So if we're looking to solve this with a table, we would be looking to see where do they have matching y values. All right. For the same x, where do they share that common y value? And in our picture, we noticed our point of intersection was -4, -2. So I'm going to scroll up here, and you can see that at -4, both of the y coordinates are -2. So that would be another indication that that is the point that they have in common. All right, so our calculator keys. Just a quick reminder, we entered the equations in our y equals screen as y1 and y2. We turned the plots off, and then we went to our table, which was second graph, and we just look up and down until we can find a spot where they match. Now, it could take you a long time if you strictly use the table feature because you don't know where they're intersecting. That's why a graph is nice, because it gives you that visual, at least you know what you're looking for. All right, our next example. This one says we're going to use a table to solve the problem. It says the diagrams show the birth lengths and growth rates for two species of a shark. If the growth rates stay the same, at what age would a spiny dogfish and a Greenland shark be the same length? So over here by the pictures, you'll notice they've given me a growth rate and a birth length. So for the Greenland shark, we are told that at birth it's 37 centimeters long. So that's my starting value. And then its growth rate, which would be like our slope, is 0.75 centimeters per year. So total length for that shark is going to be 0.75x, where x is the number of years, plus the original 37 centimeters that it was born with. Okay. For the spiny dogfish, we are told that its growth rate is 1.5 centimeters per year, and it has a starting length of 22 centimeters. Okay? So take a minute, enter these in your calculator. We're going to go back to our y equals screen. We want to clear out these two equations and put our new ones in. So the first one is 0.75x plus 37. And our second equation is 1.5x plus 22. Okay, now, excuse me. If we were going to use a graph to kind of help us figure out where these might intersect, we can start with the window that we had, but notice we're not seeing a whole lot. When we're talking about growth rates for these sharks, it doesn't make sense to think of negative length or negative time. So let's go to our window, and let's start with our mins both being zeros. We don't need the negative values. Okay, so x min and y min, let's both put at zeros. And then let's change our x max. I don't know how many years it's going to take for this, for the two sharks to be the same length, but let's extend this maybe to a 30. We can always adjust it later. Okay, I'm going to take the tick marks out that we've talked about before, so the x scale is 0. And then for y max, the first shark is starting out already at 37 centimeters, so we're going to have to make this much higher. So let's say we go to maybe 75. Okay, we can always readjust it if we need to, but let's see what our graph looks like now. All right, so we have a nice window here. We're seeing where the two lines intersect. And if we were to estimate this, remember we talked about this going from 0 to 30 and this going in the y direction up to 75. So estimating this point here will help us figure out where in the table we should look. So I would say it's past the half mark, it's past 15 here. So we could start with our table looking at about a 15 and see if we can find a spot where they match for our y coordinate. So let's go to our table. And let's scroll down until we get to around 15, and then we'll start looking more carefully. All right, so at 16, 17, they're getting closer together, but they still don't match. Keep going. There. At 20 years, they are both going to be 52 centimeters long. All right, let's look at our next example. Question 3 says we're going to use a linear regression. It says the table shows the populations of New York City and Los Angeles metropolitan regions from the census reports from 1950 through 2000. Assuming these linear trends continue, when would the populations of these regions be equal? So if we look at New York City, they are increasing, starting at around 13 million, increasing. Los Angeles started a little over 4 million, but it's also increasing. Okay, and you can see by the year 2000, they're getting closer together, but they're still not quite there. So the question is, when will the populations be equal, and what would that population be? So we are going to enter this and do some lines of best fit for each of these. For our years, we're going to go ahead and have 1950 be times 0. All right, so we're going to let x equal years since 1950. All right, so this is going to be times 0. 1960 would be 10 years later. 1970 would be 20 years after 1950. And if we keep going, we are going in 10-year increments. So for our list 1, we are going to enter those numbers, 0, 10, 20, 30, 40, 50. For list 2, we are going to enter the New York City data. Okay. Now, what we're actually going to do here is we're going to do 2 linear regressions. So we're going to enter the data all at once. That means we're going to put Los Angeles in as a list 3. Now, we've got a lot of numbers here. Instead of entering them that way, we're going to put our y's in terms of millions. All right, so for example, for New York City, the first entry in list 2, instead of this whole big number, we're just going to do 12.9 million. All right, so we'd enter that as 12.9. This one we're going to enter as 14 point, if we round up, 14.8. Okay, we don't need to be as accurate down to the individual person. All right, so I'm going to pause the video. Go ahead and take a minute and enter list 1, 2, and 3. In both cases, your populations are going to be entered as a million number instead of all of the extra digits. All right, we have taken time to enter. List 1 is our years since 1950. List 2 has our New York City populations, and list 3 has our LA populations. All right, we're going to do 2 different linear regressions. So the first one, I'm going to go to Stat, Edit. We've entered our data, so we'll go over to Calc this time. 1 variable stats again, linear regression. And for the first one, for New York City, I do want to use list 1 and 2. So I have year and population. We're going to go ahead and store this one in Y1. So variables, Y variables, function, Y1. Okay? And we're going to go ahead and calculate that. All right. So for New York City, we have the equation y equals 0.147x plus 12.886. All right, now notice the R value, it's 0.96, very strong positive correlation. This time we're going to go back to our stat key. We're going to calculate a linear regression again, but this time we are going to pair the years with the LA population. So now we want to use list 1 and list 3. So remember, I can change that list 2 by hitting second 3, it changes it to list 3. Now be careful, because in this one, I want to store a second equation. So I'm going to store this. I'm going to go to vars, y variables, function again. But this time I want to go down to y2 so that it stores this second equation in a different spot. Otherwise, it's going to overwrite the one we already did. And now we go to calculate. Once again, notice that we have a very strong correlation. For LA, our equation is y equals 0.251 times x plus intercept is 3.805. All right, so now if I look at my y equals screen, you'll see that it's put those whole big decimal numbers in there for me already. And what I want to do is find where these intersect. Okay, we are going to go to our window, and I'm going to have you set it for x's to go from 0 to 100, because we already have the data for up to 50. We know that in 50 years after we started, they still didn't match. So let's go up to 100 years. Our populations have been numbers like 12.9, 14.8. So for our y values, our population, let's say we go up to maybe 30 million. Hopefully they'll intersect before they hit that. If we can't see the point of intersection, we can always change this window and make it a little bigger. All right, let's look at our graph. And there, just towards the edge, upper right corner there, we do see a point where they intersect. Now, your calculator is actually able to tell you the exact point where those cross. To get that, I'll come back to that screen in just a second. To find the point of intersection, all right, the keys you're going to hit will be second key, and then you're going to go to the trace button up at the top, and then we're going to choose option 5, which is an intersect. Okay, so let's start there. So on my calculator, I'm going to do second, and then the trace key is up here right next to the graph key. Notice number 5 is an intersect. Now, the cursor is blinking on the first equation that was entered. At the bottom, does it say, it says first curve with a question mark. You're just saying, yes, this is my first equation that I want to use. I'm going to hit enter to acknowledge that. Now it blinks on the second, the red line, and I'm going to hit enter again. They only make you do this because in your y equals screen, there are 10 different equations. So it's basically saying, tell me which two you want to find the intersection of. Then it asks you if you want to make a guess. You can bypass this. You don't have to make a guess. Just hit enter a third time now, and it'll bypass that, and it'll give us our intersection. So looking right down here, we are given the x and y values where those two lines intersect. So our New York City and LA populations will match when x is about 87. And remember, x was years. And our y value, which is our population, was 25.6. But again, that was in millions. So to answer this question, I would say the two towns are going to have the same population of 25.6 million people after 87 years. And now we started in the year, what was it, 1950? So if we add 87 years to that, population will match in what year? If we add 1950 and 87, we're at 2037. So we can expect in the year 2037 that those two will have the same population. All right, the last little bit that we're going to talk about today is looking at the different possibilities. We've had examples where both lines have intersected in one spot. That's not always going to be the case. So we're going to classify the equations by the number of solutions. If the equation is consistent, we are looking at a system that has at least one solution. Okay? Underline that at least. Consistent means it has at least one solution. Now, within that classification of being consistent, we have two options. It might be independent or dependent. An independent system has one solution. A dependent system has infinitely many solutions. Okay? Now, if it is not consistent, meaning it doesn't have one or more solutions, we call it inconsistent. This one would have no solutions. All right, so what we would see in our picture, if we have two lines that intersect at one point, this would be a system that has one solution. So we would call it consistent and independent. We'd need both of those terms. If we have coinciding lines, that means we have two equations that really represent the same line. So when we graph them, they land on top of one another. This is where we say there are infinitely many solutions. Every point on the first line is actually going to be a point on the second line. And then this one would be classified as consistent but dependent, not independent. And then our case where we get no solution, that's where we're talking about parallel lines. So these would be considered inconsistent. There is never going to be a point where they cross, which means we can never find a solution to that system. All right, let's look at our last example here. We have the system 4y minus 2x equals 6 and 8y equals 4x minus 12. It says, without graphing, is the system independent, dependent, or inconsistent? Now, without graphing it, what we really need to look at is, do we have the same slopes? We can tell that right from the equations. If we have same slopes, we know that they're parallel, or they might be two of the same line. So let's break this down. Let's take each of these and get them in our y equals mx plus b format. So the first one, 4y minus 2x equals 6. If I were going to solve that for y, I'm going to add the 2x over, and then I'm going to divide everything by 4. So I end up with 1/2 x plus 6/4, or 3/2 if you want to reduce that. Our second one was 8y equals 4x minus 12. If I divide everything by 8, I end up with 1/2 x minus 12/8. And again, if we simplify these, 6/4 would be 3/2. And for here, 12/8 would be negative 3/2. All right, so analyzing them, they have the same slopes. Okay, so same slopes. But the y-intercepts are different. This one is at a positive 3/2. This one is at a negative 3/2. So same slopes, but different y-intercepts. And again, if we look at the pictures, that would be this situation here. They have the same slope, but they are intercepting the y-axis in two different spots. So we would classify this as inconsistent. If we had gotten two identical equations, meaning the slopes match and the y-intercepts match, then we're looking at this middle picture, the coinciding lines. Okay? And if we get different slopes, then they're going to be the first picture where they intersect. All right, that's it for our notes today. Your homework is going to be page 138, questions 8 and 9, 12 through 16, 17 through 27 odd, 29 to 32, 41 to 42, and 55 to 57. We've been looking at a lot of technology here, but keep in mind that for some basic equations, you should know how to graph them and to find their point of intersection with just a paper graph, not a calculator graph.